I wanted to briefly discuss where the Lorentz transformations come from. Basically, this is a rehash of an argument presented in your textbook, but in video form, where I can highlight which parts of the graph I'm talking about at which time. So I encourage you to look at the textbook for further details. But imagine that we have a space-time diagram, and that there's some event E that occurs over here. We'll also label the origin event O. And now imagine that we have, in addition to this home frame represented here, an other frame moving with some velocity beta. In the home frame, the time at which event E occurs with respect to the origin is just t sub e, and that should be this length as represented on the vertical axis. Now imagine that we draw a parallel now using the information from the other frame so that we figure out where the event occurs in the primed frame. We draw our parallel, and we would say that it occurs at point P on the x prime axis. So point P occurs at t prime equal to 0 at some location on the x prime axis. Now remember, the advantage of two observer spacetime diagrams is that the events we represent should be at the correct locations in both the home and the other frame on our plot. So we could go back to the home frame now and describe the time te in terms of two different time intervals. One, the time interval between event P and event E, and the other, the time interval between the origin and event P. Everybody would agree in the home frame that t sub e is just the sum of those two time intervals. Alright? Now we want to relate that to something in the primed frame, namely something in the other frame. How about t sub e prime? So that's the time at which event E occurs in the primed frame. Well, that should just be represented by this length graphically. Alright, so we'll start there. Well, my claim is, since we're relating a coordinate time in the other frame to a coordinate time in the home frame, we should just be able to use the metric equation, since both frames are inertial, to say that te prime equals delta t pe times the square root of 1 minus beta squared. Because in both cases, we're discussing time intervals between point P and point E on our diagram. Alright, if that's true, we can rearrange that and solve for delta t pe. We do that and get the coordinate time interval between points P and E in the home frame equal to gamma times te prime. Remember, gamma is just 1 over the square root of 1 minus beta squared. Well, if we do that, now we can replace that delta t pe in the top expression with our new expression gamma te prime. So let's do that. Okay, we've made some progress. We've connected the unprimed and primed frame, but we're not done. Now we're going to go to work on that second term in the top expression, namely delta t op, the coordinate time interval in the home frame between events O and P. To do this, we'll note that on a two-observer spacetime diagram, the angle between x prime and x should be equal to beta. So we label that. And now we're going to label a distance in the home frame delta x op, the spatial distance between points O and P. Well, if we do that, you can see that there's a very simple relationship between delta TOP and delta XOP, namely that they're related by a multiplicative factor of beta. So if we do that, at the very least, we can replace delta TOP in the top expression with beta times delta XOP. It may not seem like we've made a lot of forward progress, but now we'll see that we can relate delta XOP to something in the primed frame. We're going to try and squeeze in one last label on this plot, and that's for x sub e prime. So that is the location of both events P and E in the primed frame. Remember, they should have the same x prime position because that was the whole reason that we drew that parallel line to the t prime axis. So I've labeled x sub e prime over on the left. Well, we should be able to relate that to delta XOP. My claim is that delta XOP is just gamma times xe prime in exactly the same way that we related a delta t and a t prime before. Now, there's two ways to justify this. One is, once you've seen length contraction, you know this is how it works. Another way, though, is to realize that if we want a diagonal line on these plots to represent the speed of light in both frames, then that implies that the tick spacing in t and x is the same, and the tick spacing in t prime and x prime is the same. Now, the primed and unprimed tick spacings are not the same, but if you pick a frame, the tick spacing ought to be the same on both of those axes. Well, we just said that the multiplicative constant that allows us to go between the primed and unprimed time coordinates was a factor of gamma. It must also be a factor of gamma in space, and that's because ultimately you want the speed of light to be 1 in both frames. Okay, those are my two justifications for the equation delta xop equals gamma xe prime. Now we can substitute that in the top equation for delta xop, so we do that. And now we just need to rearrange this to get one of the inverse Lorentz transformations. Let's pull out a factor of gamma. And now we have the inverse transformation that allows us to take a primed time and a primed position and convert those to an unprimed time. You can go through the same sort of argument with exactly this plot. There would be more labeling. I don't want to subject anyone to that. To derive another inverse transformation, namely that x sub e equals gamma times the quantity beta te prime plus xe prime. Once you've gotten both of those, then it's a relatively simple matter of algebra to derive what we usually call the forward Lorentz transformations, namely the ones that have prime quantities on the left-hand side, which are down here for delta t prime and delta x prime. Fundamentally, we should be able to do this by drawing on a two-observer spacetime diagram and then just being very careful about converting between primed and unprimed frames.